Okay, so retro, you hear retro, it means, you think of retro clothing or whatever, basically old-fashioned stuff, right? But really, retro means kind of backwards. So, retrosynthesis means working backward from a desired oh, sorry, am I frozen? My bad here. Uh, so if you think about it, I'm a chemist and I'm trying to make a certain thing, right? That is a product of a reaction, so that is the end result, right? And you think about it, the only way to do that would be to think backwards and say, well, this is the end result of what I want. So what products do I need to combine to get this end result? And then what reactants, rather, do I need to combine to get this end result? And then you also might, in turn, need to do something to make those reactants. And it might take several steps. And in the IB world, we have to be able to do this with up to 4 steps. And it can get pretty complicated and challenging, especially, obviously, if you don't know the reactions super well. So in this section right here, we have some conversions, and it says conditions. It really should probably say reagents. Essentially, we're going to describe how to make these conversions. And in the case of the first few, those are only one step. And then in here, we're going to have to do some of the 2-step ones. So let's look at a couple of these. First one says hex-2-ene to hexane. So we're saturating that. Does anyone recall what you got to do to saturate an alkene? What you reacted with? Go ahead, Emily. Yes, and most importantly, though, you need the hydrogen too. Yeah, because we got to add the hydrogen to it. So yeah, that's correct. So what do we need? Now we want to be as specific as possible when we're doing this. So we need the hex-2-ene itself. We need hydrogen gas. We need the nickel catalyst. And it needs to be pretty hot, so about 150 degrees Celsius. So, these one-steppers, again, assuming we kind of know the reactions anyway, shouldn't be too bad. So we're trying to make hexanoic acid, hexane 1-ol. So this is one of these where we're oxidizing it. You need an oxidizing agent, but I think we should specify one. And if we have to come up with one, potassium dichromate is, whoops. A good one to specify. And you do need, so usually like if you see it in an IB question, or the term would be acidified potassium dichromate, or we can just say acid catalyst. Now, here's a situation where we have to specify the method. And the key here is whether we're going to do reflux or distillation. What do you guys think, reflux or distillation here? Yeah, you want to do reflux in this one because you want this reaction to go a long time. So all of those things would need to be there. Yeah. No, because I think in this case you just really need hydrogen ions, and so any strong acid, to my knowledge, would be fine. In some cases, though, you really do want sulfuric acid, in which case that would be mentioned. But in this case, I don't think it matters. Other questions about that? Okay, so let's look at some of these two-step ones. So it says ethene to ethanol, and so what the retrosynthesis sort of idea is that I want to end up with ethanol. That needs to be my ending point. So what you have to ask yourself is, is there something that I know that can be converted to an aldehyde? What would that be? And then if so, can I make it from ethene? And if so, how am I going to do that? So you kind of got to think about it in this direction, right? So that's why they call it retrosynthesis. What do I know that I can convert into an aldehyde? And then is that thing something I can make from ethene? And if it is, then you have yourself a method. So this is a two-step process, but I'm thinking about step 2 first. So that's why they call it retrosynthesis. Now, we do know of something you can turn to an aldehyde, which are alcohols. But again, we want to be specific. We can oxidize alcohols to either aldehyde, well, depending on the type of alcohol, etc. But depending on the type of alcohol, we can oxidize alcohols to ketones, to carboxylic acids, and so on. But in this particular instance, we want the ethanol. So you also have to think about the ethanol, rather. You also have to think about, so I want this, right? The specific alcohol that I can convert to ethanol is ethanol. So I need ethanol at the end of step 1. But once I have some ethanol, we're going to, just similar to the last example we look at, we're going to oxidize it. Going to use some acid catalyst. So again, notice I'm writing step 2 first. I'm leaving myself a little room to squeeze step 1 in there. What about this time? Do I want distillation or reflux? Yeah, I want to distill it because it turns to the aldehyde first, and I want to distill and remove the aldehyde before it's further oxidized to the carboxylic acid. Just trying to give myself a little room. Okay, so, and again, I was kind of keeping an eye in the back of my mind that I do know of a way to turn ethene to ethanol. So you got to kind of make sure you have that in your mind before you fully write this out. And so ethene, we've learned about addition reactions to convert alkenes to alcohols, and you react them with water. Now, in reality, you just add the concentrated sulfuric acid. Sorry, that's a little sloppy. So we got the ethene, we got the water. We're going to add that to concentrated sulfuric acid. That's going to add an alcohol, and it is going to make, well, in this case it doesn't matter, but it is going to add a hydroxyl group to one of the carbons. It's going to make ethanol, and then from the ethanol is the specific alcohol that we need to end up with the ethanol. Questions about that? By the way, one thing I'll say is that some of these things are admittedly a little sketchy in terms of actually working. Like, I am not going to claim that any of this stuff gives you any kind of real knowledge about how to actually do this or a way that would actually work. We're just playing a game here that IB wants us to play of putting these things together. Supposedly IB is against a bunch of memorization and all that, but especially memorization outside of any practical purpose. But I think that's exactly what they're doing here. So if you got a dad, grandpa, mother, grandma, whatever, who is actually an organic chemist and said this wouldn't work, they're probably right. I just want to make that disclaimer. In the general sense, they're right, but in the practical sense, would it really work? I'm not sure. In all of these cases, let's look at another. Let's look at another two-stepper here. So 3-bromohexane to hexanone. All right, so let's kind of think about this. So hexanone, well, that would be. Oh, by the way, it doesn't. It probably should also say 2, 3, 4, 5, 6. It probably should have a number in the hexanone. It definitely should, but the only one that we're going to be able to make here is hexanthreone, which is this one. So I got to get that, and I got to get that, even though it doesn't say, I got to get that specifically, and plus that's the only ketone I'm going to be able to make. And I'm going from 1, 2, 3, 4, 5, 6. So again, I'm thinking, what is something that I know that I can turn into a ketone? And then in turn, is that a thing that I can make from bromohexane? If so, how? So do we know of anything we can turn into a ketone like that? Yeah, go ahead, Abby. Yeah, the alcohol. Hexanthreol? Yes, exactly. So we need an alcohol right here with the OH here. And then this is a halogenoalkane to an alcohol, which I can do by an SN2. Well, in this case, it might be SN1 or SN2, but a substitution reaction, basically. We can convert this to this. So if we want to write step 2 first, I mean, you can do it either way, but you kind of have to think about it. So this is another one of these oxidation ones. Reflux, it doesn't matter here because you can't make the carboxylic acid anyway, but you're still probably going to want to heat it for a long time. Now, I wouldn't just say hydroxide ions because you need a source of sodium hydroxide. We could think about specifying a solvent, but this is a secondary one. You'd probably want some kind of like intermediate type solvent. Questions about that? So, these can get very, very tricky depending upon the number of steps and all that. And it's not necessarily going to tell you the number of steps, which makes it quite a bit easier if you know the number of steps. So, let's look at another example. Let's look at 11. Okay, so it says we're going to make this thing. Okay. What is this right here? It's an ester. So we're going to have to make some kind of ester. It's a little weird because it's, the attachment is a little bit different than we're used to as far as naming an ester. This specific type of naming is not required. So normally if it was if like the attachment was from the carbon here to this oxygen, we'd call it propyl ethanoate. But because the attachment's on the second carbon, we call it propantuol ethanoate. Again, you're not required in that name, but I'm just telling you, just FYI type thing. Okay, so we got to somehow end up with this. And it says we only have alkenes. That's all we got as starting materials, as organic starting materials. So in other words, we might have inorganic compounds, like acids, etc., things like that. But we only have alkenes. Okay, so again, the idea of retrosynthesis here is we need to think through this backwards. And so what two types of things do you combine to make an ester? Alcohol and carboxylic acid. So we need some kind of alcohol and carboxylic acid, but that's not quite good enough. We need the specific ones that would make this. And if you think about it, it would be like we got some kind of secondary alcohol here. So we got CH3COH. So if we had that, and then this would be just ethanoic acid. If we have those two things, remember they link right here. This hydrogen is lost, so that uses the hydrogen. This loses the OH, and then they make the water. So they're going to link right there, and they're going to make that thing. So if we can get those two items, then we could put them together in the last step and make what we need to make. So what we have to do is we have to think, well, with alkenes only, how can I end up with these two things? So let's just tackle this one first. So we've already seen this, that we can do an addition reaction, react an alkene with water to make an alcohol, but we need the specific one that would make this propantuol here. What alkene would that be? We need one with an appropriate number of carbons. Yeah, it would be propene. And remember, propene remember that Markovnikov's rule tells us that although it will add an OH to some degree to both, it's going to preferentially add the OH here, which is good because that's what we're trying to end up with. And then we're gonna end up using that in the last step. The very last step is going to be to combine these two items. So as I said, if we can figure out how to make those two things, then we're going to be good. So now I need to end up with this carboxylic acid, but I only have alkenes. we've never learned anything that we can make an alkene directly into a carboxylic acid, but